Hi there people. A while back I built a circuit to control this BLDC motor, closed loop, and at the time I decided I was also going to do it using a microcontroller. So I bought this PIC 40 board, and it's got a 16F877A controller on there, and I've also plugged a 1602 display into the board, and I've built this little circuit. It's just like a NAND, bit of NAND logic to drive the pins of the motor, because you've got the ACK pin and DEC pin, which you need to drive them out of phase to do certain things. We've also got a pot here connected to the one of the A to D inputs of the PIC. So I'll power it up and show you what I've done so far. Okay. Right. In this mode it's just basically on-off control, so I'll power up the motor. So in this mode there's no speed regulation, it's just fully on, and you can see the rough RPM there is around 4,000, and there's no speed regulation there at all. Alright, I'll now go into the PWM mode. I'll just reset this. Okay, select PWM. Okay, and let's bring up the pot. So as I adjust the pot, you should be able to control the speed. Okay, so as I apply resistance to the motor, you can see there's still no speed regulation there. Let's change the speed. Again, as you can see, you touch it and it slows down. And also if I change the voltage on the power supply, the motor slows down. And if I increase the voltage, it speeds up. While we're here, I'll also show one of the other features. If I push this button, it's just that's start and stop. Now if I push this button, we've got a reverse. And if I push this button, it switches on regenerative braking. Now if I push reverse, it stops immediately and reverses. So that's with the brake on, brake off. Right, now the interesting thing. Right, I'll reset this and switch to PID mode. Now this is running closed loop. Just to explain some of the stuff on the display. If it will focus. Alright, that's sort of a interpolated RPM figure, and the figure on the right there is the actual pulse count, and that's what it's using to do the regulation. So it's measuring you've got the set point, and that's what the set point is compared to. And if I put resistance on the motor now, that's actually resisting me turn it. And if I show you the power supply, and you can see it's running at 130 milliamps now, and as I put load on the motor, it's rated up to 2.5 amps at 24 volts. You can see that current go off, but I've also got an average RPM mode. I'll put that on there, so increasing that up to 2.5 amps, it's 2.5 amps now, and the average stays at around 2,500 RPM. Now, these are the PID parameters. The top left, the E is the error, and the P is the proportional part of the system, proportional, and I is the integral, and D is the derivative, and P is like what's the proportional, and it's when there's an error you multiply the error by the KP factor, and basically that produces a figure which is being used to drive the motor harder, basically, or less hard, depending on the situation. And the integral is basically, it measures the error over a period of time, and anything that's not corrected by the proportional is compensated for by the integral. And the derivative is basically it's measuring how much the speed is changing, and that compensates in that way to sort of stop the system oscillating. What I'm going to do now is just show you a quick view of the oscilloscope while I put load on the system. So you can see the current going up as I load it, and that's the point where I've overloaded it. What I'm going to do now is, because the way this is set up at the moment, is if I release it, it sort of overspeeds because the regenerative braking's off, so it can't actually slow the motor down, it can only speed it up. Just before I do that, you can have a look at how steady it is. What I'm going to do is go to ×10 on the oscilloscope, scroll all the way over here to the right, and I'll line it up with this line here. Very tricky. So I'm going to put a bit of load on it now, and you can see how much that's wiggling about, and it's pretty stable. One thing I'm actually going to do is I'm going to pause my program. So my program's now paused. See, it's like the line's drifting a little bit now. Not too badly, but what I'm going to do now, I'm going to actually put load on it. As soon as I put the slightest bit of load on it, it scrolls all over the place. I'm going to restart my program, unpause it, and that locks back in. Alright, what I'm going to do now is enable the regenerative braking. Alright, I've just turned that on. One thing I don't like about this is it's very rough, but it's to do with the way the PWM works with the motor. When the PWM signals high, it's driving the motor. When it's low, it's braking the motor. What I will show you though is, like, if I pause the program, even without the program running, it's still very rough. Still very rough. What I'm going to do is, like, unpause the program, so that's now running closed loop again. I'm going to put some resistance on the motor. So I don't know if you can see the power supply, so that's no load, and this is 2 amps, and you can see that line's not really moving that much as I load up the motor. If I've actually got a frequency generator here, that's measuring the MFG pulses from the motor. Again, I'm loading it to 2 amps there, 2.5, 2. So yeah, that's pretty good. Let's have a look at the figures on the board. Alright, on this display, I've got the average error in the top left, and the set point is 9,130, which that's a count. And you can see the integral, and the U is actually how hard it's trying to drive the motor. So as I load the motor, I'm loading it now, I've got my hand on it now, as you can see, it's starting to burn my fingers. So as I put more pressure on there, you can see the figure go up for the drive. So that's at 3 amps. That's at 1 amp now. So one thing I'll actually do is, because of the way this is set up, I can change the some of the proportional constants. Well, change all the PID constants. What I'm going to do now is, for example, change the proportional. I'm going to change it from, it's actually 12 at the moment, I'll change it to 1, and I'll restart the program. As you can see, it's gone unstable there. What I'll do is I'll change the integral to 1 and see what effect that has. That eventually stabilised. So I'm going to pause that, unpause it. It's a bit wobbly, but it's working. Okay, I've got it paused again. What I'm going to do is now change the proportional back to 12. I'm going to leave the integral at 1. What I'll try and show you on the oscilloscope is let me zoom back in on here. Okay, that's the motor FG pulse there. Again, what I'm going to do is put some resistance on the motor. See how when I put resistance on the motor, as I put resistance on, it moves to the right as it slows down, and then it pulls back in. A little bit of overshoot as well. but you can see as it takes a while to compensate. What I'm going to do is change the integral to 3. And restart the program. Now, as I put load on it, you can see how it sort of pulls straight back in, so it pulls back in quicker. I'm going to try the integral at 4, see if it's still stable. Yeah, that's worked. So yeah, it seems to do quite well. Zoom back out on that. See if that will give us a better view. The trace on the bottom is actually the PWM signal for the motor. So as I put more load on there to keep it under 3 amps. Yeah, that responds quite quickly. What I'm going to do now is change the derivative, and I'll change that down to 0, see what effect that has. Because the purpose of that one is really to stabilise the system. So here we go. I'm going to hit run. Yeah, you can see it's unstable. So that's doing its job. Let's have a look at the parameters while it's shaking like that. Yeah, the error is very high, and the proportional is high. Integrals going plus and minus. Derivative is moving around a lot. What I'm going to do is pause that and change it to, can't remember what number it was now, I'll change it to 12 and let's change this integral back to about 2. Okay, up and running again. What I'll also do is hit the reverse button just for the fun of it. Let's turn braking off. To turn the braking off, you can see it waits till the motor stops before it reverses. That LED on the left is the actual PWM LED. Okay, that's about it really. I'll move the set point just to demonstrate what that does. I'm going to change the set point from 9130 to 8000. Don't know whether the motor will run that fast. And unpause it. You can hear the speed's gone up. You can see the set point's been updated on the display. And An average error of 2. That's really good. See, average RPM 2856, and you can see the set point is 8000, and it's staying within one count of that. Let's put the regenerative braking back on, see how well it does. Yeah, it's still staying within one count. Let's put a bit of load on that. There's a little bit of wobble on that. So 8001, 2.7 amps. One amp. Yeah, that's quite reasonable. Let's see if I restart it. Okay, that's it. It's written in PIC assembler, and it's using the capture compare unit to in conjunction with timer 1 to measure the FG pulses from the motor and to measure the speed, and it's using timer 2 in the PWM module in the capture compare unit to do the PWM. And it's using quite a variety of interrupts. I think it's using timer 2 as well for housekeeping, like for checking the keys and doing things like timing RPM, etc. Things to do with waiting for the motor to stop before restarting it in different directions, etc. But it took me a lot longer to write this little program than I thought it would really. It's been a while since I've done any PIC programming, and I've never actually done a program quite like this before. Anyway, hope you enjoyed that. Thanks for watching.